tomorrow Ichiba. Okay. So let me start by having a brief review on the development of discrete time quantum walks. Okay. It's not working. Yes. Okay, so it's not working. So like for the waiting time being, so we actually recently uploaded our preprint to archive. So you can as well search this archive number for our preprint. Okay. Yes. Okay. Okay. So as I mentioned, to begin with, let's start with a brief development of discrete time quantum walks. Okay, so discrete time quantum walk was first defined by Aharonov, David Dornish, and Zagari in 1993, and they want to generalize classical random walks to the quantum setting. And it turns out that this is actually the right generalization, because in 2004, Sejindi found that for every classical random walk on a ergodic and symmetric graph, you can have a standard procedure to raise it to the quantum walk level, okay? So that the quantum walk algorithm corresponding to that quantum walk always has a quadratic speed up in terms of hitting time problems. So a standard hitting time problem is the search problem, okay? But nevertheless, so Meyer in 1996 reminded us that, so he actually termed quantum walk, not using quantum walk, but quantum walk cellular automata, to remind us that quantum walk is a deterministic dynamics. Okay, so randomness only occurs when we measure, when we do measurements. So, so now the intriguing question is, why does quantum walk exhibit the quadratic speed up? Okay, so as a mathematician point of view, we are not satisfied by just looking at the complexity analysis of that speed up. We want to really look into the dynamics on this infinite-dimensional Hilbert space. So how is there any limiting theorems of these dynamics that can help us like support this quadratic speed up? So by the way, quantum walk dynamics is as here. So it's governed by this walk operator W, which is in turn, okay, by this walk operator W, which is in turn could be decomposed into two operators, the shift operator and the coin operators. Okay, so before I talk about the limiting theorem, let's kind of visualize what a quantum walk is. So a quantum walk can be visualized as on a state space of L2Z crossing with plus or minus 1. Okay, so you can imagine we have a line of vectors. Okay, so every integer has a vectors. Okay, so and then for every integer you have a coin components there. So a quantum walk operation is consisting of two steps, the coin step and the shift step. So for the coin operation, we would apply this coin operator to these vectors. Okay, to get it to another vector, we call it tilde here, and then we apply the shift operation to shift based on this computational basis at the site. Okay, so here we are actually using E1, and we don't use the bracket notations because another goal of our paper is to kind of connect the community of probability and also quantum computing. So we use this standard basis notation corporate in mathematics. Okay, so this shift operator actually gives a right shift on the E1 basis and left shift on the E-1 basis. Okay, so we repeat these walk operations to get the n-step quantum walks. Okay, so what are the like the existing limiting theorems of quantum walks there are? So the first existing theorem is what we call the ballistic weak limit of quantum walk. Okay, so for every time n, we can actually define a random variables, a classical random variables on integers by the probability mass function coming from the sum of amplitude squares of the quantum walk dynamics. Okay, so Conrad and Grimmett and co-author independently has found that these random variables, when we scale this by a linear time n, we can actually have a probabilistic weak convergence of these random variables. Okay, so before I talk about the next thing, let me pause for a while to mention that. So in this paper, for our work, we can actually generalize our result to any kind of quantum walks, so for very general quantum walks. But for the exposition purpose today, we just focus on the quantum walk with the coin and with a rotational coin, e to the power I theta sigma 1. Sigma 1 is the Pauli X matrix, and as well as the case of homogeneous coin. So all the coins there are the same. Okay. Okay. So now let me kind of have some brief comparison between this quantum walk limit with the classical regime, classical central limit theorem. That means. So for the classical central limit theorem, we actually have the limit when we scale by square root of n. Okay. And then for this time, we have the limit with the scaling of n. Okay, so by this, we already can see that kind of have some evidence on why do we have the quadratic scaling because of this time, okay? The quadratic increase in the time, okay? And in that addition to this scaling, we see that the limiting behavior is actually very different. For the classical case, we have the central limit theorem. So the limiting density is a normal distribution, which is localized at the origin, okay? But the limit of this quantum walk is actually a ballistic, it have a bimodal behavior. Okay, so you can see from this density, when this y is closer and closer to the boundaries, okay, so you can see this fraction actually blows up. So you can visualize this density from this plot of quantum walk probabilities. Okay, so this is a very typical quantum walk behavior. We have more probability when it's further away from the initial conditions, which is 0 here. So another interpretation of this bimodal behavior is that actually we say that quantum walk actually tends to have momentum. So it tends to have memories. So how can you have this more distribution on the away from the origin? So that means you must have more steps towards the same directions. Okay, so that means you keep the momentum actually for quantum walks. Okay, so next, other than the ballistic weak limit, we have another limiting theorem, which is the continuous times PDE scaling to a quantum transport equations. Okay, so as again, we actually can scale the quantum walk amplitude using a common scaling. So we call it a probability scaling. So a common scaling for the space and time. Okay, then with some additional scaling for the coin, we can actually have the limit of this amplitude. Okay, which is the solution of this PDE system. So this PDE system is actually a quantum transport equation. It's a transport equation because we see this linear order of both space and time derivative, okay? And then you have an extra interaction, what we call the phase interaction term between these two components, okay? So this quantum transport equation was actually first rigorously derived from Morfetta and Debach in 2012, and also studied, and also people found that it's actually a special case of the common direct equation by Maeda in 2018. Okay, so one remark to this system of equation is that this system of equation is actually kind of, you can see the I here, okay, is kind of the complexification of a hyperbolic equation, hyperbolic transport equation, instead of the Schrodinger equation, which is the complexification of a parabolic of the heat equation. So this is some remark here. Okay, so what's our contribution? So this is the graph of this PDE. So you can see you have a similar bimodal behavior here. Okay, so what's our main contribution? So our main contribution is to derive this Feynman formula, okay, and to use this Feynman formula to derive the previous standard result. And then during the process of derivation, we actually see there is some, this Feynman formula actually allows us to connect this quantum walk process with some classical process, okay? So in particular, we connect this with a classical Markov additive models, okay? And through the process of derivation, we additionally find that the asymptotics of quantum walk, the ballistic weak limit, is actually related to the large deviation of this classical Markov process, okay? And additionally, this approach allows us to give a probabilistic representation to the PDE that we just seen before. Actually, so for the graph of PDE here, we actually do this graph using Monte Carlo simulation of that probabilistic simulation. Okay, so let me kind of briefly talk about this Feynman formula. So again, our assumption is the homogeneous rotation coin. So we see that the amplitude of the quantum walk can be written as a conditional expectation of this Markov additive model. So a Markov additive model consists of a triples. So we have a Sn, which is a Markov chain. So this Markov chain is a sum of independent Poisson random variables modulo 4. So this Sn is a Markov chain. And then this Gn is the function of the Markov chain, okay, -1 power. And then this Xn is the sum of a function of the Markov chain. Okay, so we see that so we call this thing a Feynman formula precisely because this is analogous to this is actually exactly the Feynman path integral, but then we can recognize this integral using a probability weight, using a probability measure. Okay. Okay. So the next thing, okay. So here is actually a subtlety. So I mentioned that we have a low-fold connection between classical and quantum process, but people may think that isn't that whenever at a time n you can define this Cn to follow this modular square distribution, and you already have a classical process. Isn't that the case? But actually no, because this random variable is actually giving you just a flow of marginals. That means just the one-dimensional random variables, but not the correlation between the random variables. So there is no stochastic process, but just a flow of one-dimensional distributions. Okay, so there is actually some existing result talking about how to fit a Markov process with this flow of marginals. Okay, so for the discrete time, we have the result by Monteiro, and for continuous time, we have the result by Eric Carden. Okay, and again, there is also another relation talking from the dynamics using open system. So for open system dynamics, we allow measurement. So if we repeatedly measure things and allow the open system dynamic to evolve, then we actually can get a classical process. But we want to emphasize that our stochastic process, the Markov additive model, is not in any case related to any measurement. Okay, this is kind of served as a probabilistic technique to deal with quantum walk. Okay, so let us get straight to the point how our Feynman formula can help us derive a sketch of how it derived the two limits that I just mentioned. Okay, so first let's talk about the ballistic limit. So actually, to better use the Feynman formula, we better define a stochastic process Tn, which is a sum of -1 to this Markov chain Sn. Okay, and then if we put the initial condition psi 0 into our Feynman formula, okay, so here, if you trust me, then you will get this at the amplitude of a quantum walk becomes the difference of a probability. Okay, and this is not an ordinary difference of probability. This is actually a difference of very small probability. Okay, because this Tn is a sum of Markov chain, sum of Markov chain states. So actually, by the ergodic theorem, this will converge to 0 almost surely. So we are actually in a large deviation regime for all these probabilities. Okay, so we are actually a difference of very small probabilities. And by the way, we remark that we have this AN scaling because of the hyperbolic scaling that we want to take care of. Okay, so the point is, how can we deal with this difference of small probabilities? So an analytic tool is that for Markov additive process is that we can actually tackle these things using the tilted kernel technique. Okay, so we can actually write this probability as the sum of spectrums regarding about these tilted kernels. Okay, so what is a tilted kernel? So for this Markov chain, so you see that the Markov chain is Sn sum of Poisson mod 4. So it's a 4-state Markov chain. So the transition matrix of this Markov chain is kind of very symmetrical and is a 4-dimensional matrix. So, and then we can tilt it by having some exponential factor here. So this is the tilted kernel. Okay, and then it turns out that due to the symmetry properties of this tilted kernel, we can decompose this kernel into two matrices. Okay, and the spectrum of that kernel actually falls into pairs. Okay, fall into AK and BK. And it turns out that for the difference of probabilities, because of the difference, the only spectrum that corresponds to the quantum walk is those spectrum from BK. The spectrum from AK got deleted because of that difference. Okay, and it actually is very interesting to us that if we do the same asymptotic analysis on the eigenvalue of AK, we actually get back the very famous large deviation property of this Markov additive model. Okay, so in short, if we do asymptotic analysis on the spectrum of AK, we get large deviation. But if we do asymptotic analysis on BK, then we get quantum walk. Okay, this correspondence is very interesting to us. Okay, so by this, we are allowed to get the ballistic scaling using asymptotic analysis, for example, using like stationary phase method. Okay. So the next thing is to see how our Feynman formula can derive the quantum transport PTE, the continuous time scaling that I just mentioned. Okay. So actually, our Feynman formula gives a really easy proof to that. Okay. It's because our Feynman formula already is written in terms of an expectation of classical process, and we actually know that for this classical process, we have the continuous time scaling. Okay, for the Sn, we scale to a Poisson process, and for the sum of this -1 to the power Sn, it actually scale to a telegraph process integral to -1 ns. Okay, so this telegraph process is called the continuous time scaling limit of a random walk, but with Markov increments. Okay, and then it turns out that by just standard result in probability, we can preserve this weak limit under this expectation, and then we get a limit like this. And after we get this continuous time conditional expectation, we can simply write the quantum PDE. Okay, just from the expectation. Just the relation is just the usual how you get from Feynman-Cat to the Feynman-Cat probabilistic equation to Feynman-Cat formula. Okay. So yeah. So now, so lastly, let me summarize and have some outlook on our work. Okay. So in fact, for as we mentioned, for the exposition just now, we just assume that we are under a homogeneous coin case with the mutation coin. But in fact, we can generalize the Feynman formula to any arbitrary unitary coin and also with inhomogeneous coin. That means all the Cx, they could be different and they could be changing over time. We can still write a Feynman formula, okay? And then we anticipate this could work on higher dimensional states and coin. Okay, that means instead of integer, we go to set 2, or instead of 2 states, we go to 3 states. Okay, and so it's actually very interesting for us to see the correspondence between quantum walk and the large deviation property of Markov chain. But then this is the theoretical interest. But then for the side of computing, for the application, this actually can raise some new insight on classical simulation of quantum algorithm. Okay, so we can write the quantum amplitude as a difference of two rare event expectation. So this, if we can do some things like importance sampling using on this area event or like bootstrap, as mentioned this morning by Professor Grisels, we may have some insight on quantum supremacy, how quantum algorithms surpass the classical algorithm. And from the continuous time scaling, we actually see that quantum walk has an interesting connection with telegraph process. So telegraph process has actually been used on option pricing by Waterloo and Kalisic. So they will actually wrote a textbook on telegraph process on option pricing. Okay, and at the same time, so Professor Orwell here also used quantum walk for pricing. And the reason he want to use the walk for pricing is that he want to capture the notion of like the momentum of the price. Okay, so this connection with telegraph process kind of gives some theoretical background on using quantum walk for pricing models. Okay, so last but not least, our ongoing work includes, but not limited to, as we said, the Monte Carlo analysis using that PDE. Okay, as well as the generalization of this Feynman formula to nonlinear quantum walks. Okay, so that means not just unitary dynamics, but maybe even open system dynamics. Okay, so basically that's all for my work, my presentations, and these are the references. And so thank you so much, and I'm very happy to take questions. And also feel free to reach out if you find my talk interesting, and I'm happy to have a collaboration with you guys. So this is my personal webpage and my archive articles here. So thank you so much.
Thank you. Any questions for Carlo?
Hi, Ka. Thank you so much for the presentation. So could you go back to that slide where you talked about using the ergodic theorem for convergence?
Yes.
Yes. So the TNs are, they converge almost surely via the ergodic theorem. I was just wondering if that's because, are they kind of like, you're taking it from the time domain to the ensemble domain and then ensuring the convergence in the ensemble domain via the strong law of large numbers? Because the ergodic theorem is just saying that the convergence in the time domain equals the convergence in the ensemble domain. Is that the idea behind it, or?
Oh yes, this is the thing behind it. Actually, another way to see the algorithmic theorem is that the sum of the Markov chain over this time actually converts to the expectation of the stationary distribution acting on this functional. It turns out that the stationary distribution here, -1 to the power sj, is clearly uniform, but we have 1 and mass 1, so it actually converts to 0.
It's because it's mass 1, sorry?
So here, the stationary distribution of this -1 Sn is uniform between 1 and -1.
Yeah.
Okay.
Oh, okay.
Yeah, and then we just convert it.
Oh, the mean is 0
expectation.
between the two.
Yeah,
Okay. Okay. Thank you.
Thank you.
Any other questions? Any questions on the? Okay. So Kalok, thank you so much.
Thank you so much.
One more time. Now we have a coffee break, but I wonder maybe